we are live right now. I will start today's lesson by recalling everyone. We covered a very important part of the material. That's a part where we discussed about product rule, the quotient rule, and we even did an application last time about the slope of a tangent line, where we actually involved a little bit of these rules right in the calculation. So right now we are at some sort of a crossroads here. So basically, we got the important rules, but we only know how to do derivatives for polynomials, essentially powers of x, folks. So we need to do a little more in order to have something more meaningful. And the next step would be to discuss trigonometric functions. And then finally, another step would be to discuss exponentials and logs, but we do not do that. Our school does not do that in Calc 1, so you will do that in Calculus 2 if you happen to take that class, which again, I will tell you a little bit about a little later. But the point is, this is that one part of the material where you need to remember some trigonometry. How much trigonometry do you need to know? Well, folks, it's not a very introductory course in trigonometry with just the basics that you would learn in high school or college algebra and trig or pre-calculus. Things like how to define sine and cosine as the opposite over adjacent. The idea of measuring angles in radians. We discussed about that in an earlier lesson. And, a couple of formulas, of key formulas that will help us get through this in a smooth way. So to make this transition smooth, or at least my hope is to make this transition smooth, because I'm not going to be able to reteach the trigonometry, section, a full section of trigonometry in just, 5-10 minutes. But you need to know some of these things, and they need to be reviewed because kids usually forget them. And, so it's pointless for me to start talking about sine, cosine, tangent, things like that when kids don't remember the connections between them. And it's also good to have everybody on the same common denominator. So even if you know these things really well, please bear with me for the next 5-10 minutes so that we can actually review what's needed from trigonometry. All right, so that's one thing that we'll do today. And then we'll discuss about derivatives of sine, cosine, tangent, such things. And we are going to do applications of those. So that's the goal of today's lesson. Now, with that being said, before I start my discussion in today's lesson, this lesson kind of ties nicely in a way with Calculus 2. So how does that tie nicely? Well, in Calculus 2, so remember, folks, in a previous class, whenever you learn trigonometry, you learned about sine, cosine, but there were some other functions which we do not study here, so they will be studied in Calc 2, such as sine inverse and cosine inverse, for example. And those are very useful there. That's because they also help with integration or antiderivatives, a concept we will discuss later in the class. And so there's a few of those, but fortunately for you, if you only intend to take Calc 1 and then finish with Calc 1, so no more math after that, fortunately for you, you don't need to know much trigonometry, which is very different from Calculus 2. So when people move from Calc 1 to Calc 2, Calculus 1 ends here, and Calculus 2 starts here in a way. So it starts at a slightly higher level. there's a gap between the two, and that is where one would have to fill in the gap with a trigonometry, which unfortunately is studied before you end up in calculus 1. So there is a time gap that I don't know how that would be covered efficiently unless your instructor in calculus 2 is willing to fill in this gap to kind of do a review, kind of like I do here in calculus 1. So whenever I teach calculus 2, I do that. I do spend maybe a day or so reviewing the important stuff from trigonometry in order for kids to kind of catch up and get started all at the same spot. Some people maybe even sometimes I assign some extra homework for those kids who have forgotten those. But certainly these are things that most likely a number of people have forgotten because it's not that you use trigonometry every day unless you are a physics major and you take a specific class that uses trigonometry like sine, cosine, and such. So most likely you have probably forgotten some of these basic things. So let's review them together. The ones that we need in Calc 1. Ones that you need in Calc 2, again, that's going to be your Calculus 2 instructor, or independently you, if your instructor assumes that you know them already from some other classes. All right, so I don't want to. What am I saying here? So seeing some news. Oops. All right, so that's unusual. All right, see some basketball stuff. Okay, I didn't want to put the news on the screen here. All right, folks. So we are going to discuss today. Let me. There's a bunch of things that popped up on my screen. So 1 second. I'm going to start with trigonometry in a second here. So let me move these things out of the way. There we go. All right. So now finally we got the right setup. All right. So a review. So before we do 2, 4. I'm sorry. Derivatives of trig functions, or we could say 2, 4. We could save a title here. Derivatives of trig functions. Oops, since I told you, and again that thing popped up here. Doesn't let me write. All right, there we go. Derivatives of trig functions and trigonometric, that is. And so there's a review. So we start with a review of trigonometry. So I should say here, not the entire thing in trigonometry, just the essential facts for calculus 1. And my hope is that your instructor in calculus 2 will do the exact same thing. So we'll do a review of trigonometry, essential facts for calculus 2, which is quite different from this one here. So this one plus some more stuff. All right, so that review would start with first of all the definition of radians. So radians, folks, we measure angles according to the arc length they describe on the unit circle. So let me explain you what that is. Oops. Okay. Come on, eraser. All right. On the unit circle. So let me explain you what that is. So let's do the unit circle over here. I'm going to do very quickly just a random, kind of looking circle. Apologies for, not having a very, very nice picture here, but you get the idea, folks. So this is meant to represent the unit circle. So this would be the number 1 here. This would be the number 1 on the x-axis. And you have an angle that's called theta over here. And we measure theta by measuring this arc here. So, so let me make that with a different color. So here's what we measure. We measure this guy here, this arc length, and that's called the measure of theta in radians. All right, and that way, folks, because this arc length, so when you have a 90-degree angle, which everybody knows what a 90 degree is, right? So so when you have a 90-degree angle, I'm going to make that blue here. So when you have a 90-degree angle like that, this would be 90 degrees, but that's not the measure in radians. The measure in radians will be, well, by looking at it this way. So we know that the arc length of a circle of radius, so circumference of circle of radius r is pi r is 2 pi r. I'm sorry, 2 pi r, right? So so this is the circumference of a circle of radius r. So when the radius is 1, the circumference is 2 pi. So that tells me that this going like this, along the circle would give you for a 360-degree angle, the radian measure will be 2 pi. For a 90-degree angle, so for 360 degrees, the measure in radians is 2 pi. And a 90-degree angle being a quarter of 360 degrees will be 2 pi divided by 4, or pi over 2. And that brings us to the commonly known, formulas for the radian measure of various angles. So 90 degree will be pi over 2. And if you do proportions out of 360, so for instance, a 60-degree angle is the sixth part of 360, right? Because 6 times 60 is 360. So, so that will be in radians will be 2 pi divided by 6, which ends up being pi over 3. So you recover the known formula. So 90 degrees corresponds to pi over 2 is pi over 2 radians. 60 degrees is pi over 3 radians. So this is in radians. All of that is in radians. All right, so so this being given in radians, that allows us to do some nice calculations, and again, calculus is based on the knowledge of radians. We will do a bunch of nice calculations to actually derive nice formulas for derivatives. All right, so this is one part. Now the next thing that I want to do here, and let's change my color again to black from white. The next thing that I want to review is sine, cosine, and tangent based on a triangle. So on a triangle, so this is the famous Secant rules. And this means sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So so this means that when you have a triangle, say something like this. So let's make the triangle the other way around. Oops. Come on, triangle. All right. So so let's make the triangle this way. So so this is an angle of theta, and this is 90 degrees here. So 90 degrees or pi over 2, right? The sine of theta is opposite. Or let's call that. You know what? Let's see. Let's call that. Let's give them some names. A, B, C. So sine of theta is going to be BC divided by AC. So opposite over hypotenuse. This guy is called hypotenuse here. And so cosine theta is the adjacent over hypotenuse. So is AB divided by AC. And tangent of theta is opposite over adjacent, so it's CB divided by AB. There we go. So that's the sine, cosine, and tangent formulas. Yeah. So this is more or less what you need to remember from working with trigonometry in triangles. All right, so this is okay. Number two thing that I wanted to review, and there's two more things that I will review here. The number three thing that I will review today is, folks, and I want everybody to pay attention to this aspect as well. Angles can be interpreted in the unit circle, so very important. So let's go back to the unit circle, and you know what? Let's let me at least draw this circle nicely here, because I don't like ugly circles, but this software. Well, there we go. Oh, it looks like a circle. Okay, so there we go. I got a circle. I got lucky there. All right. So let's do something that looks like the y-axis, and there we go. So approximately we're in business there. All right. So that is the x and the y-axis. And let's see what happens with these angles. So when I draw the angle, and I can also make a straight line here. There we go. So let me see what happens when I calculate. So this is the angle theta over here, and now I can interpret sine and cosine on this circle. How do I do that? Well, I look at the point here. This is important point here, and I say that because of the construction that you saw earlier. So let me do that with red. So if you drop a perpendicular like that here, folks, and you get a 90-degree angle here, then you will see that this triangle here that I'm going to shade with red right now. I don't need to shade it, but you know that's an important triangle. Well, does have an angle of theta here. So I can express sine theta as the opposite over hypotenuse. But the good thing is that on the unit circle, this is 1 here, right? This is 1 and this is 1. On the unit circle, so again, the unit circle is the main character here in a way. On the unit circle, the hypotenuse is 1. So sine theta really turns out to be the adjacent, the opposite over 1. And the opposite is the y-coordinate of this point here. So the y-coordinate of this point here, which is this much, the red segment going down, is the y-coordinate of this point, which is called, I'm going to call this point A, is a y-coordinate of A. And cosine theta is similarly is going to be this guy here divided by the hypotenuse, and it's going to be the x-coordinate of the point A. So that's so this point A, you can say, has coordinates cosine theta comma sine theta, because the x coordinate is cosine here, folks, and the y coordinate is this one here. So that is very important, and if that's the case, then you can also say, oh, and the tangent, folks, would be, and you can see here that tangent from any of these two would also be, and this is another trick here. So I'm going to draw this with, let's say, different colors. So let's put green here on the picture. So I'm going to draw a line here, tangent to the unit circle through this point here. And if this line intersects my line OA, let's say this is O here. So this would be B over here. So if I intersect there, then I can look carefully here and I can see that tangent is in this slightly bigger triangle that ends up with the green side. Here is the opposite of theta, which is this one here, divided by the adjacent. But the adjacent turns out to be 1 because the radius of the circle is 1. So tangent of theta is I would say y coordinate of B. So it really represents the rise of B from the distance from B to the x-axis. All right, folks. So this is the third thing that I wanted to review here from trigonometry. So don't forget that, because we will use interchangeably these things. So we will use this point of view and the point of view with triangles, which you know they are connected. And finally, this kind of longish and I hope not too boring review of trigonometry, folks. You know, I apologize for those of you who already know the stuff really well. I am going to discuss about some special values, special values and identities, which you would need to know. So let me first say some identities. In fact, let me start with identities. Useful identities. So these are useful for Calc 1. There's others that are useful for Calc 2, but fortunately in Calc 1, we don't need to even remember the double angle formula, although that would be nice to use. So we only need to remember this one: sine squared theta plus cosine squared theta is equal to 1. So if you square sine and cosine, this is equal to 1. Why is that? Well, that's called the Pythagorean identity, and you can guess easily that because of the presence of the name of Pythagorean identity. All right, because of the presence of the name of Pythagoras here, that really is the Pythagorean formula. So if you go back, look at this triangle here, the one with red. So sine squared is this side squared, cosine squared is the horizontal side squared, equals hypotenuse squared, which is 1 squared. So that's the Pythagorean identity. All right. I hope everybody remembers that. So again, whenever you see sine squared plus cosine squared, that's also the same as 1. And finally, there's another one that is very useful here. So the relationship between tangent and sine and cosine, and in fact, that tells me that in a way, sine and cosine are the bricks of trigonometry, because if you have those, you have every other function there, in particular tangent, which is sine theta over cosine theta. So if you want to see why that is true, again, go back to your red triangle here, and you can see that sine theta over cosine theta is opposite over adjacent, and that is tangent. So tangent is that. All right, and this is pretty much, folks, I would say that's pretty much all you need to remember from trigonometry. Perhaps, I forgot this one. This is another important one. Secant theta. So you need to remember what secant theta is, which is, remember, 1 over cosine theta. So these three, these three, I would say, are the key formulas that you wanna manipulate with these. So when it comes to applying some derivatives for these kind of functions, there's something you wanna manipulate with these. All right, there's other formulas, but I would say that these are the key ones, and that's kind of what you wanna refresh your memory on these three. All right, finally, some special values. And if something else comes along, then I will review that at the time. But I think this is pretty comprehensive what we need. So it's a little fast, but I believe that if you learn trigonometry recently or maybe within the last year or so, with this review, you can go back to your textbooks. Hopefully you have them. I think there's a review of trigonometry in this textbook as well somewhere, or at least some review of formulas. So let me just quickly look here. Okay. Well, so should have been some areas and some other things, but no. All right, so apparently not. That's okay. I forgot to look it up, but again, So again, if you need any more help on trigonometry, then I will go over those things at the time when they are needed. Or you can ask me and I can help you more with that. During office hours and things like that. So special values here, folks. This is what we started. So let's not lose track of those. So I would say even among these special values, there's a couple of them that are really super important. So everybody needs to know that, for instance, cosine of zero of the cosine of theta, no, not that. Let's start with sine, in fact. Sine of zero, the easiest of all is zero, folks. Sine of zero is zero. Cosine of zero turns out to be one. Again, if you've forgotten those, oh, this is a good time to remember. All right, sine of pi over 2 or sine of 90 degrees is equal to 1. And cosine of pi over 2 is equal to 0. Now, folks, how do you quickly review these if you've forgotten them? You look at the unit circle. And folks, sine of 0 means the rise when your angle is 0. When your angle is 0, it means your angle is something like this. So there's no rise, so that's going to be 0. All right. Cosine, on the other hand, is the length, the distance from your point on the circle from here to the origin. So that's why it turns out to be 1. Likewise, sine of 90 degrees, your rise is going to be at this point here is 90. Your rise is 1, and your displacement from the y-axis is 0. All right, so that's sine, that's cosine. All right, there's a few others that would be nice to know. So for instance, I'm going to point this out. Sine of pi over 4. By the way, that's a 45-degree angle, folks. Sine of pi over 4 is the square root of 2 over 2. Cosine of pi over 4, similarly, pi over 4 here, square root of 2 over 2. And tangent of pi over 4 is the quotient of these, but because these are equal is 1. This is actually really nice to remember. Tangent of pi over 4 is 1. There's a few more. So for instance, let's say sine of pi over 3 or sine of, let's do sine of pi over 6. It's very similar to this one. Sine of pi over 6 is 1 over 2. And cosine of pi over 6 is square root of 3 over 2. And that's about right. So then you have sine of pi over 3, which is square root of 3 over 2, and cosine of pi over 3, which is 1/2, is these two here at the bottom switched around. Those may be needed at some point, but I would doubt we will use much of those. So normally people in this class will kind of appeal to this here, maybe this one over here, rarely the one at the bottom here. So I'm just reviewing those here for you, just so you have an idea. If you want to play with these things, construct the triangle with a 60-degree angle and a 90-degree angle, and you will see, you will figure out the values on your own there. So it's not too difficult. All right. So that being said, this fast speed review is finally over. Do you folks have any questions before we move on and we actually discuss plain and simple derivatives? All right, so seeing that there are no questions here, I am going to now move on and do derivatives of such things. And as it comes to derivatives, well, here's another thing that I did not review in the first part here, but it's important, and I will review it with this occasion. So the graph of sine, what does that look like? Well, the graph of sine, folks, would be, when you plot the sine values, so you plot the angle here on the x-axis and the sine values on the y-axis. And because sine goes between -1 and 1, and is 0 at 0, we just review the value at 0, it will always go through here. And all you have to remember is that the shape is a wave. So it goes up and down and up and down, and up and down periodically, and it repeats this pattern, repeats itself every 2 pi, because once you make a complete rotation, you get the, the values of sine and cosine repeat themselves. And you have the exact same situation if you go on the in the opposite direction. So you repeat this pattern forever. So this is the graph of sine over here. And it intersects here at pi because sine of pi is 0. And it has a maximum here at pi over 2. Folks, you can look at the symmetry of this graph, and it really has a bunch of nice things. This is 3 pi over 2, pi over 2, pi, 3 pi over 2. So, so there's a little bit of symmetry that can guide you as where these intersection points are. All right, so with a graph of sine, let's take a look at derivatives, right? So we want to do y equals sine x. We want to calculate y prime. What is y prime? Well, y prime, for y prime, we are going to repeat an exercise that we carried out in the first part when we discussed about derivatives. We just defined them, and we said, you have to look at the slopes of a tangent line. And it appears here that the slope of this point at 0 is actually 1, because it's like halfway, So, so that's the slope, and then the slope goes down, and you go a little higher, and it becomes 0 over here, horizontal, right? When you get to pi over 2. So if we were to represent this thing, on the on a similar graph underneath, I'm going to say here, you know what? I started at 1 with a derivative, and then I went down and down and down, and I sort of went to 0 here. And then if I continue with the slope of a derivative as negative, then really negative over here. So which would, by symmetry, you could say, well, if this slope was 1, this one over here at pi would be negative 1. So, so the graph will go down, 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 and we'll get a value of negative 1 over here at 3 pi over, oops, I'm sorry. So, okay, the graph doesn't look particularly nice. So let's redo that. Sorry about that, folks. So I'm going to do it again. I'm going to squeeze it a little more so it reflects parallel here. All right, so there we go. So we want to, this would be my my pi over 2, right? And this one down here would be pi somewhere here, and this one would be 3 pi over 2 and 2 pi. Let's say that. So we go down. So let's go again. So we, as we said, we go down. So 1 here, and then go towards 0. And then we go to 0 here, and we go down, and we go to negative 1 over here. But then after we pass negative 1, we slightly, it's still negative, but slightly increasing until we get to 0. So then we go here, there we go, and then we continue with a graph like that. It's going to be again all the way to 2 pi. At 2 pi, we get again 1. And then we continue decreasing, and this pattern is going to repeat itself. So, so if you look now, so this is the derivative, this is the y prime graph over here. So if you look at your trigonometry and you review graphs, I did the graph of sine here. The one that's over here, folks, is nothing but the graph of cosine. So, so surprise, surprise, when you do derivatives with functions, sine and cosine substitute each other. So, so y prime is equal to cosine. Oops. Hang on a second, folks. Come on. Give me the eraser. Okay. All right. So, so this is cosine of x. All right. So this is the first basic formula, and I will write it here. And in the book, he says d over dx of sine x is equal to cosine x. And personally, I don't like to denote derivatives like this. So what I would like to say is sine x prime is equal to cosine x. So this is a formula that I want you folks to remember either in this form or in this form. I told you that there is a logic to writing this symbol d over dx. It's kind of old-fashioned if you ask me, but there is a logic to using that, especially for differential equations. But I like to write things up with derivatives with a prime symbol just like this because it's easier. It's kind of more compact, and it's to me it's kind of easier to kind of see. Sine prime is cosine. Some people simply say sine prime is equal to cosine. All right, now if you perform a similar calculation, folks, you will see that the derivative of cosine x, d over dx of cosine x, turns out to be negative sine x. So in other words, cosine x primed turns out to be negative sine x, or people would say cosine prime is, negative sine. It's easy to see again on the graph. So let's go back to the previous page. Now this is the graph of cosine over here. We decided, right? So if you do derivatives for the graph of cosine, well, here's what you will do. You do slopes of tangent lines, and it's 0 here, so it starts at 0. But then as you go down, 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 you go to -1. So the graph of this derivative will be, if I represent here a quick sketch, so I start at 0 and I go down, 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 -1 and go like that, and it's going to be clear, another wave. But this wave here that I get, as you can see, it's going to be exactly the negative of this one, of the one earlier. So that's why it's a negative sign, because it goes down first instead of going up. If we went the other way, if you went this way, then it would be just sine. So that's why the derivative of cosine, folks, is equal to negative sine. And these two, there's another one that we'll do to end the lesson with. These two here are the key formulas that you should never forget. So sine prime is equal to cosine, and cosine prime is equal to negative sine. So don't forget this. So do not forget. You will be tested on these on various, exams, quizzes, and such, all the way through Calc 1, Calc 2, and so on. So this is not something that if you forget these, then you won't make much progress in Calculus 2, not even in this class, let alone Calculus 2. So folks, very important formula. Do not forget. All right, so to end the lesson today, I am going to show you how to calculate the derivative of tangent. So let's say we have a function y equals, I'm sorry, so let's write here. So equal to tangent of x, and you want to calculate y prime, and you say, well, wait a second. So if I want to do y prime here, do I have to do that graph with the, the tangent graph, which, by the way, so I didn't review the graph of tangent, but here's what it looks like. It will look something like this. It's a horrible situation, because if you try drawing tangents, you will not recognize an easy formula. So the only option is here, and fortunately the thing that saves the day is one of the formulas we just reviewed at the beginning of the hour, and it's that instead of writing tangent, I could say sine x over cosine x. And guess what? I can calculate the derivative of that, because if I know two functions and their derivatives, yeah, sine prime is cosine, cosine prime is sine, then I can do the derivative of a quotient with the quotient rule. So yeah, that quotient rule that we just learned like an hour or two earlier, that's the thing that we are going to use here. So let's happily here apply the quotient rule and finish up our lesson. So y prime is equal, and by the quotient rule, I'm going to say QR here. So, so the top primed will be sine x primed times cosine x. Remember to use quantities, minus sine x times cosine x primed. So folks, this is the derivative. Remember, f prime g minus f g prime. That applies to trigonometric functions, those rules. They do apply. So, so that's going to be divided by cosine x squared. And this is going to be, folks, this is going to be sine x primed is simply cosine x. And I'm going to have cosine x times another cosine x from here minus sine x times sine x. Well, is it correct here also? So let's see, sine prime is cosine, right? So we get to took care of this properly, but this one here, sine x times for cosine x primed, I have to be careful. I have to put negative sine x. So I'm going to put a minus sign over here in front of it. Now, in order to make that more visible, let's leave a little more here, and let's say times negative sine x. All right, and all divided by cosine. Folks, people write, instead of cosine x squared, they will write cosine squared x. Just to avoid some confusion, because some people tend to leave out the parentheses, and then you think it's x squared first, and then cosine applied to that or something. So there's all sorts of confusion that can occur, and you don't want to get into any sort of trouble like that. And I will show you folks here how this really turns out into a nice formula, because if you write a formula, you will see cosine here. Cosine is cosine squared x. And over here you have a minus, and times another minus is going to be a plus. And then sine times sine is going to be sine squared x divided by cosine squared x. And at this point, there are two ways to break up the formula. One way would be, and this is what majority of people do, they will say, oh, I recognize very quickly here, and let's look here, back to the review. Where did we review these things? So look here, sine squared plus cosine squared is 1. So I learned that, the Pythagorean identity. Well, that's exactly the thing that I need here. Cosine squared plus sine squared is 1. So you can say, well, this is 1 over cosine squared x. And some people will recognize, oh, but didn't we call 1 over cosine? Didn't we call that secant? Yes, it is secant. So then this one will be secant squared x. And that's the formula that a lot of people like to memorize and use in practice. But guess what? This is not the entire story, because if you move on to calculus 2, that there's another formula that's going to be important there. And really, we don't use this in Calc 1. So somehow our class is designed to be, so free of this formula really entirely. But if you break up a sum here, so if you write cosine squared over cosine squared, the plus sine squared over cosine squared, you know what? You can notice that these guys cancel out, and that's going to give you 1. And these guys here is sine over cosine all squared, so it's 1 plus tangent squared x. I'm sorry, I said x, but I wrote theta. All right, so so this is another formula that's going to be useful in Calc 2. So this is useful in Calc 2. This is used in Calc 1. All right, so that's different uses for the two formulas. So you could use this here, but it's a bit more cumbersome. So people usually come back to this one. So so our last formula today, and this is where my lesson will end. is this one here. And the last formula says tangent x prime is equal to secant squared x. And this is another formula that do not forget. So so this is the third key formula for me. All right. And I'm going to point out that there is a nice table in the book. So I'll close my lesson with this comment. There's a table on page 148. And that table gives you the derivatives of the trigonometric functions. You may want to mark your books if you bought your own textbook. That's a page you want to mark because you will come back to those formulas time and time again. So in that table, there is a left side and a right side. On the left side is the three formulas we did today: the derivative of sine, the derivative of cosine, and the derivative of tangent. And everybody needs to remember what's there. Now, depending on the instructor, so some people, so different people have different policies. In my class, I will say you don't need to memorize the formulas on the right side of the table. That's the derivatives of cosecant, of secant, and cotangent. There's the co-functions, so-called co-functions, because you will not use those very often in practice. However, you need to be aware of those, and I will do a derivative calculation tomorrow where I will prove one of those formulas. But again, they don't need to be memorized. Now, some instructors are more ambitious. They will say, no, you gotta memorize this formula. So it's up to you. If you feel like you should memorize those, memorize. But again, it's something that you most likely will forget. The thing that is coming to be an issue sometimes is that in calculus 2, you might run into some of the other formulas, those three on the right side. So it's useful to know them. But again, even in calculus 2, I would normally say, you know what, I can tell you what the derivative of that is, and then just move on from there, because there's a lot of other concepts that you need to learn there. I wouldn't want to be stuck with just that thing there. So remember this table on page 140. That's what you should bookmark. All right, folks. Now I'm going to stop the recording here. I don't want this lesson to be too long. And